Welcome back to Hypothesis Testing Part 3. We've been looking at the case where we know what the population standard deviation is, and we've created confidence intervals in hypothesis testing based on a sampling distribution which is normally distributed, where we know what the standard error is of our sampling distribution. Well, now we're going to look at the case where we do inferences about the mean in a more realistic situation where sigma is unknown. So the conditions for inference that we're going to talk about, most of the conditions will look the same. Data from a simple random sample or randomized experiments of size n, that our sample size is less than or equal to 5% of the population. The population has a normal distribution with a mean of mu and a standard deviation of sigma, or samples are 30 or more. That will ensure that the sampling distribution is normal or approximately normal. Both the mean and standard deviation are unknown for the population, so we use inference to estimate the mean, mu. But the problem here is sigma is unknown. And that means we can't use our Z procedures that we've previously learned. So now we're going to talk about something called the student's t-distributions, or t-distributions for short, that will help us to do these inferences, and why. So first, let's just talk about t-distributions and why they're so important when we don't know what sigma is. Well, the sampling distribution of the sample mean for particular sample sizes is close to normal. That sampling distribution is close to normal or is normal. We can find probabilities involving the mean. And we know that. We standardized our values, our means, by this z-score. It would take our sample mean minus the mean of the sampling distribution, which just equals the mean of the population, divided by the standard error, which we know to be sigma divided by the square root of n. And we could use our standard normal table to find probabilities of certain means occurring or between two mean values. But what happens now is, what if we don't know what sigma is, and we're estimating sigma with the sample standard deviation? We no longer have these clear lines and these clear probabilities, because now we're estimating sigma, the population standard deviation, with the sample standard deviation. So there's going to be a wiggle about that line. So we're going to have some new statistic to take into account this estimation or this wiggle or this cloudiness, because we're guessing what sigma is. And that is what we're going to learn is the standardizing, and we're going to have to use what's called the student's t-distributions. And there are many, in fact, infinite many, student t-distributions. So when we don't know the population standard deviation, we must estimate it with the sample standard deviation. So now, what is this sampling distribution going to look like? What is this wiggle about sigma going to do to us? And can we compute probabilities? So when the standard deviation of a statistic is estimated from data, the results we know is called the standard error. And the standard error will look like s divided by the square root of n instead of sigma divided by the square root of n. So this is what the t statistic looks like. See how much more cloudy it looks. It's not as tight a distribution as our standard normal. And here, let's take a look at what's going on with that. So here we have a sampling distribution of the sample mean. And again, we don't know exactly where the mean of that distribution is of the sampling distribution. We know that it equals the mean of the population. And remember, that's what we're trying to estimate. And let's say this is really where sigma is, one standard deviation away. And this is really where two population standard deviations is away. And henceforth being -1 standard deviations away, -2 population standard deviations away. What's happening is, in our sample, we are estimating sigma with s. And with each sample, we're going to get a different estimate for that sigma. So here's our standard deviation from sample 1. Here's our standard deviation from sample 2. Here's our standard deviation from sample 3, and so forth. We keep wiggling around this first standard deviation, and we do that, and that would be the same. We're going to have that wiggle room around here. So this distribution with each different sample, depending on where it is, flattens or gets taller. So our distribution wiggles around quite a bit. So we have a fuzziness to the shape of our distribution. What we find is we're going to have more probability in the tail ends, which makes sense. We've got this wiggle going around, some a little bit greater than where the standard deviation is, and a little bit less than where the standard deviation. And that's what this means in your PowerPoint that you saw. That's why this is so much thicker and so much more probability in the tail end. And it's not as high as what the normal distribution would be if we knew what the standard deviation is. It's just a thicker distribution, more probability in the tail ends. And what does that give us? If you think about this logically, it actually should make sense. If I'm guessing what the standard deviation is, don't you think my confidence intervals should be a little bit larger? In other words, I won't be as precise because I don't know what the population standard deviation is. So my confidence intervals get larger. So they're not as precise. Now, if I knew what the standard deviation is, then I could kind of nail exactly where it is, and we can have more precise confidence intervals. And if I want to reject a null hypothesis, it will take a little bit more to reject it because I don't know what that population standard deviation is. So for each sample size, the larger my sample size, the law of large numbers tells us that my guess gets better. So guess what happens to these distributions, to these student t distributions here? As my sample size gets larger, my guess for my standard deviation gets better, and these thicker distributions start to look more like that distribution, the standard normal distribution. So what would that look like? So as my sample size increases, so this is this one, we'll say that this is a sample size of 10. If I did a sample size of, let's say, 40, I'm going to have a different student t distribution because my guess for the population standard deviation with this sample size is going to be better, and the distribution will still have some dots in here, but it's going to get closer. It won't get quite up to the standard normal, but it's going to get really, really close to the peak there, and it won't be as you see this one, it won't be as thick in the tail ends. It will be thinner, and it's going to look more and more like the normal distribution that we see here. It's going to thin out. So most of the probability, we won't have it being so thick in here. It's going to be a little bit thinner in here. And as my sample size increases, we're going to find out. So if n gets to be, let's say, 1,000, my student t distribution is going to look very, very similar to that distribution. It's going to get very tight, and it's going to look almost exactly like the standard normal distribution. And in fact, we find out that as n gets very large, student t distributions converge to the standard normal distribution, or in mathematical terms, it gets closer and closer to it as our sample size increases. So for each different sample size, we're going to have what's called a specified degree of, and as you can see, as the student t distribution, the degrees of freedom get greater. As the degree of freedom gets larger, so here's a degree of freedom of 2, is this red line right here. It doesn't peak. It peaks much lower than the actual standard normal. The dark line is the standard normal curve. it can't peak as high, and we have more probability. Look at all that probability, much more probability in the tail end compared to the normal distribution here. As my degree of freedom increases, look what's happening, which is this green line right here. It's starting to come down to where the standard, it's starting to come up to where the standard normal distribution is, and there's much less probability in the tail end than the degree of freedom of 2, and it's converging, it's getting closer to what the standard normal distribution looks like. So what's a degree of freedom? A degree of freedom, which is abbreviated DF, is just your sample size minus 1. So as your sample size increases, your student t distribution starts to look more and more like the normal distribution. So our one sample t statistic looks like x bar minus mu, our standard deviation from our sample divided by the square root of n, where in order to use our standard normal table, we need to know the degree of freedoms. And we said the degree of freedom is n minus 1. So using the student's t table, you're going to have degrees of freedom down that left corner for the table that I give you. The table that I provide for you is very nice because it's going to give you a lot of information. But first we're going to learn how to use it. So on the left-hand side is your degree of freedom. Remember what that is. It's just your sample size minus 1. And your confidence level is along the top. And what we do is, let's say that our sample size was 12, okay? So if our sample size was 12, our degree of freedom is 11. So we go to 11, and then we look for the proper confidence level to find the critical value. So for a 95% confidence level, so this column right here would be your 95% confidence level. That's the critical value that goes with a 95% confidence level. Is this, and remember, with our z for a 95% confidence interval, alpha over 2, it was 1.96. So remember, our distributions are thicker, so our critical values will be further out in the tail end, and they get closer into the center of the distribution as n increases. But this is a relatively small sample size, so you see there's a pretty big difference in here. So now it's time in our PowerPoint that I had, where you had to go and look in the table to find the critical value for a 90% confidence interval with these degree of freedom. So the sample size for this was 7. The sample size for this was 17. And this, it was 18, excuse me. And the sample size for that was 26. And if you look in your, if you take out your student t distribution, which you ought to do right now, you're going to find the answers to these, the critical values for a 90% confidence interval for these different degrees of freedoms or sample sizes. And hopefully you can do that. And in the PowerPoint, we do it for a 90% confidence interval, then for a 95 and a 99. And you should be able to get these critical values. You should be able to find the same critical values in your student t distribution. Very, very nice exercise to do. Now, as you look in your student t table, and you can see this converging of the student t to this normal distribution. Check this, and this is very clear right here. As you can see, as my sample size increases here, it's increasing. It's going from 9, 15, 41, all the way to 1001. And of course, these are the degrees of freedom that go with it. 9 minus 1 is 8, 15 minus 1 is 14, and so forth. We can look at the 95% confidence interval, the critical values that go with that, and look what's happening to them. They get smaller and smaller as my sample size increases until they converge to what it is for this normal distribution. So 95% confidence intervals, we're going to look for a sample size of 41 and look at the difference. That would be, as you can see, for a sample size of 41, this is 2.021. But the real, in a normal distribution, is 1.96. So we can see clearly that for student t distributions, the confidence intervals are a little bit greater than for the standard normal. So we're guessing what the population standard deviation is. So we want our confidence intervals to be a bit larger so that we can make sure that we capture that mean in there, or hope to, at a 95% confidence level. In other words, that this procedure will work 95% of the time. And in order for it to work 95% of the time, we need to make those intervals a little bit larger. So what happens, they say n is when doing these rough estimates by hand, the normal critical values can be used if n is really large. And for sample sizes of 40 or more, you can actually estimate the student t critical values with the standard normal. They call these large sample confidence intervals in hypothesis testing. So many books will start out, even if we don't know what the population standard deviation is, they'll start off with large samples so that you can just do the standard normal distribution in order to find probabilities. I like to teach it this way because truly, if you don't know what the population standard deviation is and you've got technology, you should be using the student's t distribution, because you can even see back in here that even at 1001, if you need to be very accurate, you'd be off by the 10,000th place. And there are some times, depending on what your measurements are, that could make a difference. If not, then just use the standard normal for these large sample sizes, because after 40, they get very, very close to 1.96. So, don't want you to get confused now with 40s and 30s and things like that. So remember, we can't forget that if we don't know the population standard deviation, we need to be using the student's t distributions. They are like the normal distribution, like normal distributions want to be, except for that we don't know what sigma is, so we have to widen our confidence intervals. So all the conditions that we needed for the the technique that we just got through learning have to apply to the student's t. You have to have normality established. So if I don't know what the population standard deviation is, I have to have sample sizes of 30 or more to evoke the central limit theorem, and then I use my student's t tables if sigma is unknown. So when a sample size is small, particularly let's say n is 10 or something like that or less, or the level of confidence needs to be high, particularly 0.005 or lower, these are where we find that the t and the standard normal distributions differ quite significantly. And let's look at this example. For a sample size of 5 for a 99.9% confidence level, the t critical value is 8.610. So we have to go with this 4 degrees of freedom compared to the normal critical value, which is 3.291. That's a pretty substantial difference. So when our sample sizes are very small and our confidence levels are very high, student t and the standard normal differ quite amazingly. So please, let's not forget the conditions for inference about the mean. When sigma is unknown, we still need data from a simple random sample or randomized experiment. So our sample size has to be less than 5% of the population. The population has to either have a normal distribution, so that my sampling distribution will be normally distributed, or my sampling distribution has to come from samples of 30 or more, so the central limit theorem can be evoked. so that that sampling distribution of the sample mean is normal or approximately normal. It is normal if my population's normal. It's approximately normal if I don't know anything about the population or know it's not normal and I have sample sizes of 30 or more. Then we don't know what sigma is, so we'll have to go to the student's t-distribution. So the way that we make confidence intervals will be, the technique doesn't change. I still have to get the sample mean. I add and subtract a margin of error. So here's that margin of error is right there. Hold on, I just got, so you can't see that. Sorry about that. But here's your margin of error is right there. That's the critical value that comes from the student's t-distribution. And people call it just the t-distribution for short. And instead, remember, we don't know what sigma is, so we use the sample standard deviation, and we divide it by the square root of the sample size. And remember, to get that critical value, we need two different pieces of information. So I always like to write it like this. You need to know the confidence level and the sample size to get the degree of freedom. So in the chart, you'd have to look at 90%, but you also need to know what the degree of freedom is, the n-1, in order to use the student t-distribution. So we have different critical values for different sample sizes. So we're going to look at an example, and we're going to calculate the 90% confidence level. So a manufacturer of high-resolution video terminals must control tension on the mesh of fine wires that lies behind the surface of the viewing screen. The tension is measured by an electrical device with output readings in millivolts. A random sample of 20 screens have the following mean and standard deviation. We want to find the true tension, mu, of the video terminals produced this day at a 90% confidence level. Now, if I just looked at this problem, let's see. We have a random sample of 20 screens, and many of these are being made so we know that the first two conditions are met. But is the third condition met? We have a random sample of 20, but we don't see anything in here that the output readings are known to be normally distributed. So at this particular time, we'd say, we can't do this problem. It's just, we can't do it. Well, that's not exactly true anymore. So we're going to learn that if we have the raw data, we might be able to do this problem because we can do an analysis on the data. And if my sample that I took, the sample that we're seeing right here, the sample of 20, if that sample, after a data analysis where we look at the box plot, normal probability plot, is what we use in our class. Some people look at dot plots and things to see if the data can be reasonably considered normally distributed. So that's where we're going to learn how to do probability plots and box plots. So luckily we had the random sample of 20 screens and we could look at the data. And this is what we look for. In a normal probability plot, we look to see if the data runs along a line, a straight line like this. Oops. And if the data does, then we can say, okay, based on this probability plot, there doesn't seem to be any deviations from normality. Now, sometimes when you see the data, it will look like this. It will have some strange bow to it, or you'll have data points way far away that could be outliers. That's why we do a box plot, to make sure in Minitab we don't see any astrophyx, okay? So the normal probability plot will tell us that there are no deviations from normality. And the box plot ensures that any of this like that isn't an outlier. So the box plot, we make sure there aren't any outliers. So, and this is the dot plot, which you're kind of seeing that the data sort of runs along here. Dot plots are a little bit trickier because they're harder for people sometimes to tell. So these two are really great ways to see if there's any deviations from normality, and that's what we use in our class. So based on these graphs, I don't see any major deviations from normality, so it is reasonable to assume the sampling distribution is approximately normally distributed or is normally distributed. So now, if I've got the raw data and my sample size is less than 20, I can see if it looks relatively normally distributed, I can use my techniques. And in this case, since I don't know what sigma is, I have to use the student t-distribution. Now, since we've established that our sampling distribution is approximately normally distributed, now it's time to look at how do we find the critical value. Well, again, since we don't know what the population standard deviation is, we have to go to the student's t-distribution. So for a sample size of 20 that we see right here, the degree of freedom is our n minus 1, or our 20 minus 1, which gives us the degree of freedom of 15. Now we need to find the critical value for a 90% confidence level. So that's where these two intersect. So my critical value is 1.729. So really we need two pieces of information to find the critical value, the confidence level and our sample size, to find that critical values. I think in your PowerPoints, these numbers down here were incorrect. They're corrected here. I'm going to repost the PowerPoints to make sure that you guys have those right things, but this is the critical value for 90% confidence interval when we have a sample size of 20. And so now we just put our sample mean in there, that critical value we just found from the student's t-distribution, and there's our sample standard deviation. The whole reason why we had to go to the student's t is because we didn't know what the population standard deviation was, and we had to use this sample standard deviation, which causes a little more wiggle. And there's the square root of the sample size. So here is our confidence interval. So with this technique, this works about 90% of the time. That will really capture the true mean. If we did everything correctly and our sample was randomly selected and there were no incorrect inputs of data or anything like this, this technique works 90% of the time. Now in this next example, we have heights. Heights are generally considered normally distributed, so we know all sampling distributions are going to be approximately normally distributed. And we show a 95 and a 90, we show a 95% confidence interval, how we would calculate it. And it's the same thing. We go to our chart, we go to degree of freedom of 6, and we look for the critical value that goes with a 95% confidence interval, and it's 2.447, and we calculate our confidence interval with our sample mean plus or minus. So in here we see our sample mean right there, plus or minus. This came from the standard normal table. So this is for a 95% confidence level with degree of freedom of 6. And we multiply that. We take this, we multiply it by the standard deviation from our sample, divided by the sample size. And that's where you got here. And so we get this confidence interval. Again, this technique works 95% of the time. Now we can use Minitab to help us find these confidence intervals, and also looking at the output of these. So we're going to look at, real quickly while I'm in Minitab, we're not only going to look at doing the confidence interval, but we're going to look at a hypothesis test in there. So our first thing is we're going to use Minitab to find the 95% confidence interval for the same problem that we just did, where our sample mean was 67.2, our sample standard deviation was 3.9, and we're doing a 90. Well, let's do a 90% confidence interval. Since we already have the 95, we're going to use Minitab to find the 90% confidence interval. And you had to do this for the one Minitab that you just completed. But I want to make sure that we look at the output, because it's going to be very important. You're going to have output on your final exam and have to know how to read it and use it. Because really, most of the time people use statistical software packages to do data analysis. So we're doing a one sample T. And in here, we don't have columns of data. We have summarized data. We know our sample size, American adults, sample size of 7. The mean of that sample was 67.2. And our standard deviation, our sample standard deviation was 3.9. And Minitab's default is a 95% confidence interval, but I wanted a 90. So I need to change the 95 to 90. Hit OK, and out pops my confidence interval. So there's what my confidence interval is. 64.3 to 70.1 is the 90% confidence interval that we hope captures the mean, that this technique works about 90% of the time. So we would say that the mean height is between 64.3 and 70.1 at a 90% confidence level. Now, we've already gone over, if my sample size is small and I don't know that the population is normal, the ways that we're going to check in our class for normality is by box plots and normal probability plots, both done in Minitab. So we're not going to draw them by hand. We're going to have Minitab take the data and do it for us. So what we find is, and Minitab is very nice because it gives you this 95% confidence range of values. These blue lines right here. And basically what I tell my students all the time is, if my data lies within those two blue lines, then it's reasonable to assume that your data is normally distributed. So these are this saying that it's 95% confident that our data is normally distributed is kind of what that means. So our data doesn't seem to have any major deviations from normality, and this one looks a little bit far away from the other values. So is that an outlier? If it's an outlier, then even though this plot looks somewhat linear, outliers destroy everything. You got an outlier, can't do the technique. So we got to make sure that that's not an outlier. So that's when we do a box plot. And this is showing data that's clearly not normally distributed. It's bowed. It is data that, and it's actually, when it's bowed down like that, it's right skewed. If it was bowed this way, it would be left skewed. So if any of our data is bowed, definitely not normally distributed. And if it's the sample size of 30 or less, we wouldn't use this technique. So here's we're going to look at this battery life example. And first we're going to see, is this data normally distributed? So we use Minitab to do that. And when we see the data points are in there, and really none of those look far away from each other, but we do our box plot just to be thorough, and we see there are no asterisks. And when we do our confidence interval in Minitab, this is what we get. For a 90% confidence interval, it's 8.2 to 10.7, and mean is a mean number of hours the battery will last at a 90% confidence level. And then we did a 99, and you can see as we do the 99, our confidence interval gets larger, as we would expect as our confidence level gets greater. And we have our confidence level right there, 7.3 to 11.7. Hypothesis tests are generally done the same way as all of them as what we've done before, except for once again, we go to the student's t-distribution. But we might find a little bit more problem with that because given a particular test statistic, we might not find it in the body of the student t-distribution. So a lot of times we have to do what's called capturing a p-value, a technique in which we're not going to be going into in the class. You would be given a output in Minitab and have to look at that and look at the p-value to see whether you would reject or not reject the null hypothesis. So what does all that mean? Well, if we use the classical method, we certainly can find critical values based on a right, left, and a two-tailed test. And if you take out your student t-distribution, down at the very bottom, it says one-sided or two-sided. The one-sided is if it's a left tail or a right tail, and the numbers in the body of your student t are your critical values. So what does all that mean? Well, if you look at your student t table, as I said, on the top are the confidence levels, but if we're doing hypothesis tests, we look at the bottom. And in here, when we see one-sided, this is for a left or right-tailed test. And these numbers are two-sided for a two-tailed test. And this is how it works. If I'm in a right-tailed test, so my alternative is mu is greater than mu naught. My sample size is 25. So my degree of freedom would be 24. And I have an alpha of 0.1. Well, I'm in a one-sided test. I want a significance level of 0.1. So I have to look at my degree of freedom of 24. And where these guys intersect, that's my critical value. So T critical is 1.318. So if my test statistic is greater than 1.318, I would reject H naught. Okay? And for a two-tailed test, this table makes it very easy for us. So if my alternative is the mean doesn't equal some value, and let's say my sample size was 15, so I'm looking at degree of freedom of 14, I would go and I'd say, okay, we're in a two-sided test, and my alpha, let's say, is 0.05, so I'm right here now. And I'd have to go up here to degree of freedom of 14, and my critical value is 2.145. So for two-tailed test, we get a critical value of 2.145, or remember, because we could look at either tail, negative 2.145. That means if my test statistic is less than 0, I'm looking in the left tail, I'm going to use that critical value. So if my T naught is less than my critical value, I would reject the null hypothesis. Now, if my test statistic was greater than 0, then I'd use my positive critical value to do my test, and I would say T naught being greater than my critical value, I would reject. That's using the table to find our critical values. And as you can see with our table, we don't have, for every test statistic, we don't have a critical value, we won't have the critical value in here. So we could only capture the p-value. So that's where we would use technology. So looking at this example, we have these oxygen, dissolved oxygen. We're looking to see if the mean dissolved oxygen is less than 5. If it's less than 5, it puts aquatic life at risk. So we're testing to see if aquatic life is at risk. We see that the data is normally distributed, no outliers, so it's reasonable to assume that our sampling distribution is normally distributed. However, we don't know what the population standard deviation is, so we're in the student's T distribution. So if we go and we actually, by hand, get the test statistic, and this is a left-tailed test for a sample size of 15, so our degree of freedom is 14, that's my critical value is negative 1.761. And now it runs just like a normal when we were working with the normal distribution. If my test statistic is less than my critical value, then I'm going to reject the null hypothesis. But as you can see, my test statistic is not less. T naught is not less than my critical value, so I don't have enough evidence to conclude that the mean is less than 5. So what does that mean in the context of this problem is we don't have enough evidence to conclude that the mean dissolved oxygen level is less than 5 milligrams per liter. So our aquatic life doesn't seem to be in danger. Now, a consumer advocacy group claims that the octane in a manufacturer's gasoline is less than 87. It's stated 87. The testing organization takes a sample of 40 and finds that the standard deviation is 0.5 and the sample mean is 86.86. Is there enough evidence to support the claim that the manufacturer has overstated their octane level? And we can do this in Minitab. We can actually get this output, and we don't have to do the commands. We can actually put this in. We find a p-value of 0.04. So it does seem that there is sufficient evidence to support the claim that the octane manufacturer is less than 87. So we could get them in trouble for overstating it. So in the Minitab output, what you would look for is 0.042. Now, once again, if I don't show you that p-value and I give you this test statistic, you could find the critical value at a 0.05 significance level for a sample size of 40. And let's say that it was even less than a 40, because it's easier to read the table that way, and you could see if you would reject or not reject the null hypothesis. But that's how you would use the output in Minitab. So this is a quick look at when we don't know what sigma is, and some of the same techniques that we've done here apply when we do the difference of two means, whether it's dependent or independent. With the dependent case, it's just like the one sample mean that we just completed here. You're just doing it on the differences. For the two sample, there's actually a different way that we calculate the test statistic, and the standard error, that is really the big difference. We still go to the student t-distribution, but those same techniques that we've learned from the very beginning still apply. So we can do it for difference of means, independent, dependent, and as we saw for one sample, not knowing the standard deviation. And of course, we've done it when we knew what the standard deviation was. So thanks for watching, and we will be looking at chi-square goodness of fit test last.